Good afternoon, everybody. Thanks to the Dr. Sudarshan for his invitation, and also greetings to my fellow panelists and to the audience for being present here. So I guess I had sent a few slides, but they're very much a high-level overview. So I think nothing is lost in their not being here. If they arrive, I'll probably use them. If not, I can just build on what Professor Veni Madhavan had spoken, and also my friend Mr. Animesh. So the main point, as already stressed by, there's an overview that was given by Professor Veni Madhavan, and one thing that stands out is that quantum random number generators and quantum key distribution are already visible successes. So probably many in the audience, though you don't have exposure to quantum technology, you're already aware that quantum random number generation and quantum QKD have been great successes, and we do have a representative of an Indian company, TACBit, who are in that technology. So the main question then now, in as far as I understand, in the quantum key distribution area, becomes one of how to increase the range of quantum, the secure distance of quantum key distribution. Now, one can make use of quantum repeaters. So classically, you're all aware that you have repeaters where you can have these links through which you can boost the signal, and for a point-to-point communication, then you can use these repeaters to have very good communication. But in the quantum case, you have the quantum information is quite fragile, and as a result, you have a massive loss of information. Now, the information loss is not just through what you would call the classical noise, which would be which I would call as decoherence, normal decoherence, but there's a very quantum kind of noise called dephasing. So because of these two kinds of noises, quantum signals can get rapidly degraded. So quantum repeaters is the go-to technology then that we would want in order to have end-to-end quantum communication, say across maybe 1,000 kilometers. Now, quantum repeaters are a tall order with the current technology that we have. So even if we look at the top quantum cryptographers in China, maybe Switzerland and the US, I don't think they are really up to the mark as far as quantum repeaters are concerned. Yeah. So the other one, again, the big technological breakthrough that can help quantum key distribution is satellite technology. So here the idea is that you do not send them through fibers, or you do not send them through free space communication at the atmospheric level, but instead you would make use of satellites to beam down entangled photons, and that would go to end users who can then set up measurements, local operations, and classical communication, and then establish, once you establish entanglement that is reasonably noiseless, then that can be the basis for all sorts of further communication processes. Yeah, so I'll very briefly talk about the issues that come up here. One is something which is called the PLOB bound, and how a very recent, I would say, cute and simple method to extend the range, the secure distance of quantum cryptography has been proposed, and I think that's a very interesting direction that might be explored both theoretically and also technologically. So PLOB stands for Pirandello, Lorenza, Ottaviano, and Banchi. So, but it's just called the PLOB bound, or PLOB bound, if you like. So, I mean, here, as you know, the next generation of quantum technology is going beyond the current successes of QRNG and QKD, is that we want to have a quantum internet, and also we want to have a fully secure quantum communication. In that, we might also throw in a quantum internet of things. But the key immediate challenge is extending the secure distance of QKD or quantum communication. And the obvious things is that we need satellite technology or quantum repeaters, but as I said, they're very difficult to implement. So are there simpler ways? And So before we go into simpler bounds, the first question to ask is how far can I go with the simple technology? By simple technology, I mean just end-to-end communication without using quantum repeaters or quantum technology, using a lossy channel like an optical, optical fiber. So the PLOB bound is what comes in, and what they essentially prove is that you have something like this number that you can take is like 1.44 tau, where tau is the transmittivity. So their point is that asymptotically, the key rate scales linearly with the transmittance of the channel. So an idea, so the idea for that remained for 5 years is that this is a bound that could not be overcome without repeaters. So that is where a square root improvement over it was proposed by the idea of a twin field system. And so the idea here is that you simply have Alice and Bob who send very weak quantum fields to each other. And yeah, so you can look at this figure that I've adapted from the figure at the bottom. So you have a source from which you just have, you have Alice and Bob on each side, and each of them send towards a central station a weak optical field, and the person, Charlie, who is at the center, will combine these fields and make a measurement. The key point is that these optical fields are very weak, and the measurement that he makes would be a single photon interference or followed by a single photon detection. As a result, when you have a detection that gives rise to a signal, you would have a single photon from one side and a vacuum from the other side. And as a result, you just need to, the degrading can only come from the party that contributes the single photon. So you see, you have a doubling of the distance for the same transmittance. And so that, if you like, is the origin of the square root improvement of transmittance. So having weak optical fields and single photon interference and single photon detection. So the graph here basically shows how this method allows you to go beyond the PLOB bound that I just proposed, that I just mentioned, but it is still lower than even, even if you have a single repeater as your link. So that would of course still give you a better performance, but as I said, we want to try to push the limits of our current technology without using repeaters. Yeah, the other point is that even here, because you have these two Alice and Bob sending these optical signals to each other, you need a very strong phase matching requirements and alignment requirements are there. And so that would have been a weakness of the twin field approach. So there was a modification of the twin field approach that, that was proposed recently, which is, I think, rather awkwardly, despite its highly innovative cleverness, called the sending not sending protocol, where earlier I mentioned about how Alice and Bob send to each other weak optical fields, but here the theme is the same, but instead the signal is read off, and the theme also remains the same in that it is about single photon interference and single photon detection, but rather than to both send fields, the data that's read off is based on whether one person sending and not the other person sending. So, after a bit of public announcement and classical post-processing, they will choose only those data from which one person, for which only one person transmitted the field and one person didn't transmit the field. And in this case, it turns out that because it is premised on one person sending and one person not sending, these phase errors and alignment problems don't arise. Anyway, so that's just the overview of it. So I think that this twin field and its variants have a lot of, will I think have a great future as far as quantum technology is concerned. Thank you.